So today we're going to be working on Lab 5. It's the series DC circuits. So the focus of this exercise is an examination of the basic series DC circuits with resistors. A key element is Kirchhoff's voltage law, which states that the sum of the voltage rises around a loop must equal the sum of the voltage drops. And the voltage divider rule will also be investigated. Now you can see I have some reference sections. This is from Schaum's Outline Basic Electricity 2nd edition. And what we want to do is we want to check out voltage, current, and resistance in series circuits, polarity of voltage drops, total power in a series circuit, and voltage drop by proportional parts. So this is the book I'm using for my reference. It's Schaum's Outlines Basic Electricity 2nd edition. And it's only $22 US, so it's fairly inexpensive to purchase. So you can see Chapter 4 is direct current series circuits. So you can see in a series circuit, there's only one path for current to flow. And they give you the formula for the total resistance. It's going to be equal to R1 plus R2 plus R3. So the total resistance that this circuit sees is the addition of R1 plus R2 plus R3 in a series circuit. So then they look at what the total voltage is going to be in a series circuit, and Kirchhoff said the total voltage is going to be equal to the sum of the individual voltage drops. So in a series circuit, you go up so many volts, and then you drop so many volts from the first resistor, so many volts from the second resistor, so many volts from the third resistor. So the sum of the circuit should add up to 0, or the voltage drops across each of these resistors should add up to the total applied voltage. They give you the formulas for the voltage drops across each resistor, and you can see that I is identical for each of these formulas because it's the same current running through each resistor. They give you the total voltage is going to equal the current through the series times the total resistance. So you can solve for I will be equal to the total voltage applied to the circuit divided by the total resistance. They give you a nice example in the book, and it's set up the same way we're going to do it in the lab. And you can see they have the voltage applied and the individual resistor values. So the first thing they're going to do to solve this is to find out what the total resistance is going to be. And the total resistance is going to be the sum of R1 plus R2 plus R3. The next step that they tell you to do is to find the current. And you can see the current is equal to the total voltage divided by the total resistance. And once you have that current, it's the same current going through each resistor. So now you can calculate each of the individual voltages. So figure 4.7 talks about the polarity of voltage drops. So you can see you have the positive of the supply, so the first resistor, the top, is going to be the positive, the bottom is going to be the negative. And that continues the same way throughout your circuit. The next section in the chapter we're going to look at is total power in a series circuit. So you can see the total power is equal to I times the V total, and the total power is equal to the individual powers dissipated by the individual resistors. The next section in the chapter is voltage drop by proportional parts, and I'll show you an example of that in the second half of the lab. But V, which is going to be your voltage drop on an individual resistor, is equal to the resistance of that resistor divided by the total resistance of your circuit times the applied voltage. So the voltage drop on a resistor is proportional to the resistance of that resistor compared to the total resistance of the circuit times the applied voltage of the circuit. So in the theory overview, we can see a series circuit is defined by a single loop. in which all components are arranged in a daisy chain fashion. The current is the same at all points in the loop and may be found by dividing the total voltage source by the total resistance. The voltage drops across any resistor may then be found by multiplying that current by the resistor value. And an alternate technique we can use is the voltage divider rule. This states that the voltage across any resistor is equal to the total voltage source times the ratio of the resistance of interest to the total resistance. So for equipment, we're going to be using the adjustable DC power supply, and that's going to be the Agilent E3630A. Don't bother putting the serial number down because that's hard to find. For the digital multimeter, we'll use the Mastech MSM9803. Once again, don't bother with its serial number. And then we're going to measure our resistors to find out what their actual resistance is going to be. And you can see that I've gone out on the internet and tried to find you a graphic of each of the resistors that we're going to be using today. So you can see we have the 1K, the 2.2K, the 3.3K, the 6.8K, and I put down the color codes for you. Now on the next page we have a schematic, and then we're actually going to build two circuits today. So we have figure 5.1 and figure 5.2. Do not mix the two circuits up. I've also done a complete simulation of our first circuit for you, showing you the placement of the ammeters and the placement of the voltmeters, and it shows the readings that we should expect to get when we do our experiment. You'll notice the current going through the circuit is 1.542 milliamps, 1.538 milliamps, 1.539 milliamps. Ideally, they should all be identical current, right? Because it's a series circuit and there's only one current going through the circuit. So I would record all of these as 1.54 milliamps. The voltage drops, you can see on the first resistor it's 1.5 volts. The next resistor it's 3.3, and the third resistor is 5.1. And if you add those three voltages together, it should add up to the 10 volts that is on our supply. I've also labeled the positive side of the supply being red, coming from the 20 volt terminal, and all the plus signs are going to be the red terminals on our ammeter. It's going to be the milliamp hole, and the minus signs are going to be the black common terminals. So we've got all these pointing in the right direction. The only thing to note is you only have one digital multimeter on your bench top, so to take all these readings you're going to have to move your meter around the circuit. So in the procedure, step number 1, we're going to use an ohm meter to check the values of the resistors and record your values under equipment. So under equipment, I've recorded the model number for the power supply and the model number for the digital multimeter, Xing out the serial number since they were too hard to locate. So to measure resistance, I have my digital multimeter set to the ohm symbol. I'm using the red lead in the red hole with the little ohm symbol in it, and the black lead goes to the common terminal. I have my 1K ohm resistor between two alligator leads, because if I touch the leads it will change the resistance. And you can see my reading is 0.978 k ohms. So in proper engineering notation, I label my 1K ohm resistor as 978 ohms. So my next resistor is the 2.2K ohm resistor, and you can see it reads 2.15 k ohms. So the actual value of my 2.2K ohm resistor is 2.15 k ohms. My next resistor is the 3.3 k ohm resistor, and you can see that it reads 3.38 k ohms. So the actual value of my 3.3 k ohm resistor is 3.38 k ohms. And my last resistor is supposed to be 6.8 k ohms, and we can see it's 6.7 k ohms. So the actual value of my 6.8 k ohm resistor is 6.73 k ohms. So I've recorded the values that I measured for each of my resistors, and I've kept the number of decimal points to 2 to keep them consistent. Now that I'm finished with the measurements, I've placed my resistors in a piece of unused foam so that they don't roll around and I lose them. You can see I'm starting at this side with the 1K, the 2.2K, the 3.3K, and finally the 6.8K. For Lab 5, under Procedure, I've updated Procedure Step 2, 5, and 6 to include the total resistance of Circuit 5.1 and the total resistance of Circuit 5.2, as we need these to do our calculations. We're also going to measure the total resistance of the circuit of Figure 5.1 and the circuit of Figure 5.2 to make sure that we've hooked up our circuit correctly. So under Step 2 of Procedure, using the circuit of Figure 5.1 with R1 equal to 1K, R2 2.2K, R3 3.3K, and our applied voltage of 10 volts, we're going to determine the theoretical circuit resistance and record it in Table 5.2. So this is Figure 5.1 that we're going to wire up, and these are the points. A point, B point is between resistor 1 and resistor 2, and C point is between resistor 2 and resistor 3, and D point is basically at your ground. So at D point we're expecting 0 volts. At A point we would be expecting 10 volts because that's what they told us to set our supply at. So to begin with, what we're going to do is write down on our schematic our known values. So in Figure 5.1, my first step was to write down the known values, the 10 volts, the 1K, the 2.2K, and the 3.3K. So in a series circuit, the total resistance is just the addition of the individual resistors. So in this case, we're adding 1K to 2.2K to 3.3K and coming out with 6.5K ohms. So you can see I've modified Table 5.2 so that we can put in total resistance under theory as 6.5K ohms. So under Procedure, step number 2, once you've calculated the total circuit resistance, we can now calculate the total circuit current and power and record these in Table 5.1. So my first step was to find the total resistance of the circuit, RT. So my next step is to use Ohm's law, where V equals IR, rearrange my formula so that I equals V over R. So that's equal to my 10 volts divided by my 6.5K, which equals 1.54 milliamps. Sometimes students have problems trying to figure out when to use E and when to use V. E is the applied voltage. V is usually used for voltage drops. So over in Table 5.1, we can now record the total circuit I theory as 1.54 milliamps. So my next step is to calculate the total power. And remember, the power formula is equal to V times I. So I take my 10 volts, multiply it by 1.54 milliamps, and the result is 15.4 milliwatts. So in Table 5.1, under total power theory, I record 15.4 milliwatts. So under Procedure Step 2, we're now going to construct the circuit, but do not connect the power supply. We're going to set our DMM to measure ohms, and we're going to check the total resistance of the circuit. We're going to place the DMM probes from point A to point D, and we're going to measure the total circuit's resistance, and we're going to record this value in table 5.2. Now I have one binding post connected to the red lead, and you can see I've left just a little bit of wire exposed there so I can see that I am making a good electrical connection. Now my red wire is going to come up and connect to my first resistor, which is a 1K ohm resistor, and you can see I've got it in the same horizontal row. Now my 1K ohm resistor has to connect to my 2.2K ohm resistor, and you can see they're in the same horizontal row. And then my 2.2K ohm resistor has to connect to my 3.3K ohm resistor, and you can see that they're connected in the same row. And then the back end of my 3.3K ohm resistor connects to the black lead that goes to the other binding post. In this case, I'm using the yellow binding post for my black lead. So I have my circuit connected. This is the 1K, the 2.2K, and the 3.3K, and I do not have my power supply connected to it, so I'm going to hook up the DMM across my circuit now. So with my DMM set to ohms, you can see the total resistance is 6.51K ohms. So on table 5.2, I record my total measured resistance is 6.51K ohms. So if the measured value of figure 5.1 is very close to the theoretical value we calculated, then we know that we have the correct resistors in our circuit and we've wired them up correctly. So under step 2 of procedure, we're now going to connect the power supply with E equal to 10 volts. Set the DMM to read DC current and insert it in the circuit at point A, remembering that ammeters go in line, and require the circuit to be open for proper measurement. So I'm going to show you how to do that. And the red lead should be placed closer to the positive source terminal, and we're going to record this current in table 5.1, and then we're going to repeat the current measurements at points B and C. So you're welcome to reference my simulation here. We can see that the positive is going to come from the 20 volt terminal, and that's going to go to the positive or the milliamp hole on our ammeter, and the negative of the ammeter is going to come to our resistor at 1K, and the other leg of the 1K is going to go to the 2K, and the other leg of the 2K has to go to the 3.3K, and the last leg of the 3.3K comes back to the common of our power supply. So one of the first things you should do before you wire up a circuit is get the correct voltage on the power supply. So we're going to turn on the power supply. We're going to set the meter to the plus 20 volt meter, and I'm going to adjust the plus 20 volts till I get to 10 volts. So they want me to put 10 volts into my circuit. The closer you get to 10 volts on the meter, the more accurate your readings are going to be compared to what you calculated. So we're going to take it out of the plus 20 volt terminal, and the common is the return terminal. So we need to hook up the ammeter first. So we're going to go from the plus 20 terminal into our ammeter. So that's the red milliamp hole. We're going to set our ammeter, and our ammeter is all manual ranges, so we're going to set it to the highest range possible. In this case it's the 400 milliamps because we're using the milliamp hole. If we were to use the amp hole, we could only use the A range on the digital multimeter. So we're using the milliamp terminal. So we have to select the range as 400 milliamps, 40 milliamps, or 4 milliamps. So you always start with your highest range, and you can put the backlight on for the display if you can't see it. Now we're going to use another lead to come out of our ammeter and go to our first resistor. And our first resistor is the 1K ohm resistor. And we already have it connected to the 2.2K, which is connected to the 3.3K, which comes back to this black wire. So from the black wire on our circuit, we're going to run a banana lead back to the common on our power supply. So you can see on our meter, on the 400 milliamp range, we're getting a current reading of 1.5 milliamps. Since this is a lot lower than the 400 milliamps, we can go down to the next range. So on the 40 milliamp range, we're getting 1.53 milliamps. This is still a lot lower than the 40 milliamps that we can measure here. So now we're going to go down to the 4 milliamp range. So on the 4 milliamp range, we can see we've got a reading of 1.515 milliamps. So the 4 milliamp range is the most accurate range to use. So in table 5.1, I record my measured I at point A as 1.515 milliamps. So to measure the current at point B, I have to break my circuit and insert the ammeter. So I have to disconnect the lead from resistor 1 to resistor 2. That's between the 1K and the 2.2K ohm resistor. So when you're making changes to your circuit, it's always a good idea to turn off your power supply first. Now we're going to disconnect the ammeter. So I'm going to take out the red lead from the common, and I'm going to take out the red lead from the milliamp and put it into my circuit. So now I do not have an ammeter in my circuit at all. So my next step is to put the red lead in the milliamp hole and another black lead in the common hole. So I can now take these two leads with the alligator clips on and put them in my circuit. So I'm going to show you where to place these in the circuit now. So this is a close-up of my circuit. This is the 1K ohm resistor, and this is the 2.2K ohm resistor, and this is the 3.3K ohm resistor. You'll notice the 3.3K is still connected to the 2.2K, but now I've spaced my two resistors apart so there's actually a break in the circuit, and now the ammeter is going to complete the circuit. So what I've done here is I've connected the red lead to an alligator clip going to the leg of my 1K ohm resistor, and I've connected the black lead to another alligator clip going to the leg of my 2.2K ohm resistor. So now the break in the circuit is bridged together by the ammeter. So I'm going to put the power back onto my power supply, and you can see the reading is 1.515 milliamps, exactly what we had before. So in table 5.1, under measured I at point B, I record 1.515 milliamps. And between resistor 2 and resistor 3 is C point. I have now reconnected my 1K to the 2.2K ohm resistor, and I've now made a break between the 2.2K ohm resistor and the 3.3K ohm resistor, and I've bridged that gap with the ammeter. And once again, you can see my current is 1.515 milliamps. So on table 5.1, under measured I, point C, I record 1.515 milliamps. As you can see, the current at each point is identical, as we would expect in a series circuit. Moving on to step 3, under procedure, we're going to be using the theoretical current found in step 1. Apply Ohm's law to determine the expected voltage drops across R1, R2, and R3. We're going to record these values in the theory column of table 5.2. Then we're going to calculate the total of this column and record it on the last row. So using Ohm's law, V equals IR, V1 is going to be equal to I1, which is IT in a series circuit, so that's 1.54 milliamps, times R1, which is 1K. So the voltage drop that we expect to see for V1 is 1.54 volts. So in table 5.2, under voltage for R1, the theoretical value is written down as 1.54 volts. So the voltage drop across R2 is going to be equal to the current through I2, which is the total current in a series circuit, 1.54 milliamps, times R2, which is 2.2K, so V2 is equal to 3.39 volts. So in table 5.2, under voltage for R2, the theoretical value will be recorded as 3.39 volts. So the calculation for V3 is equal to the current through R3, which in a series circuit is the total current of 1.54 milliamps, times the value of R3, which is 3.3K. So the voltage drop across resistor 3 is equal to 5.08 volts. So in table 5.2, under voltage R3, the theoretical value is written in as 5.08 volts. And then in table 5.2, we record our total, and you can see our total is 10.01 volts, and the 0.01 was caused by a rounding error, probably when we calculated our total current as 1.54 milliamps. So under procedure, step 4, we're now going to set the DMM to measure DC voltages, and we want to measure the voltage drop across R1, R2, and R3, and record these results in table 5.2. I just want to show you that I've removed the ammeter from point B, reconnected my circuit, removed the ammeter from point C, and reconnected my circuit. Now I'm ready to take some voltage measurements. So what I'm going to do is I'm going to turn on my digital multimeter, and the first V with a little sine wave after it is for AC volts. The next stopover is volts, and it's got a flat line, so that's for DC volts. I'm going to turn on the backlighting. You'll notice my voltmeter is reading something already, but there's nothing plugged into the volts or the common. So it's just picking up a signal out of the air, and it's always going to be millivolts, really small, and that's your cell phones and your TV stations. So it's just picking up random noise. So I'm going to plug the red lead into the hole labeled volt ohm, and the black lead into the black hole labeled common. So this is my first resistor. This is the 1K ohm resistor, and it's labeled R1. To measure the voltage across R1, I have the red lead going to the top of my resistor that goes to the power supply. I have the black lead going to the bottom of my resistor that goes closest to ground. Now keep in mind, our digital multimeter on the voltage range is auto ranging, so it's automatically going to select the best range, and you can see here it selected the 4 volt range, and it's reading 1.541 volts. So in table 5.2, I measure the voltage drop across R1, and I measured 1.54. I'm just going to keep 2 decimal places, so I'm going to drop off the 3rd decimal place. So to measure the voltage drop across R2, you can see I have the red lead going to the top of my resistor which is closest to the red lead coming in from the power supply, and I have the black lead on the other side of my 2.2 k ohm resistor, closest to the common from my power supply. So this is the voltage reading for V2, 3.316 volts. So I'm just going to round that up to 3.32 volts, just so I can keep them all at 2 decimal places. And to measure the voltage drop across resistor number 3, I have my red lead on the top of the 3.3 k ohm resistor and the black lead on the bottom of the 3.3 k ohm resistor, closest to the common of the power supply. This is the reading for V3, or the voltage drop across R3, 5.16 volts, and notice it's gone up one range. It's now on the 40 volt range. And my last reading, the voltage drop across R3, I recorded as 5.16 volts, and remember the auto ranging moved it up one range to the 40 volt range. And you can see my total came out to 10.02 volts, and that's close enough to the 10 volts that we calculated in theory. So if any of these numbers are way off, you would have to go back and recheck your power supply to make sure that you are putting in 10 volts. And then make sure that you do have the right resistors in there, because these numbers should be fairly close to what we calculated. By now you know how to calculate deviation and power, so I'm not going to do that with you. So under the procedure step 5, we're now going to move on to figure 5.2, which is going to be our second circuit. They want us to do all the calculations using the voltage divider rule, and we're to record all these in table 5.3. So on step 5 of the procedure, I've modified it from its original format. We have to calculate the total resistance before we can use the voltage divider rule, so I've said in here to determine the total resistance of the circuit, and we're going to record that in table 5.3. So this is figure 5.2, and I've written on all our known values. So you can see that we're going to put 20 volts into the circuit. We're going to be using a 1K, a 2.2K, a 3.3K, and a 6.8K ohm resistor. Now they want us to calculate what the voltage is going to be across R1, R2, R3, and R4. They're also asking for the voltage AC. So this is point A, and this is point C, so VAC is going to be R1 plus R2. And then they want us to calculate the voltage at point B. So point B is with respect to ground. So it's going to be the 2.2K plus the 3.3K plus the 6.8K that the voltage is measured across. So for a series circuit, RT equals R1 plus R2 plus R3 plus R4. So in this case it's 1K plus 2.2K plus 3.3K plus 6.8K, and the total resistance ends up being 13.3K ohms. So you can see I've modified table 5.3 so that we can put in our total resistance under theory as 13.3K ohms. So the first step is to calculate RT, and I've got RT equaling 13.3K ohms. So V1 is equal to the ratio of R1 to RT, so that's equal to 1K divided by 13.3K times the 20 volts, so we're expecting to see 1.5 volts dropped across R1. So V2, the voltage drop across resistor 2, is going to be equal to 2.2K divided by 13.3K ohms times the 20 volts, which is going to work out to 3.31 volts. So V3, the voltage drop across resistor 3, is going to be equal to 3.3K divided by 13.3K times the 20 volts, which equals 4.96 volts. V4, which is the voltage drop across resistor 4, is equal to the 6.8K divided by the 13.3K ohms times the 20 volts, which equals 10.23 volts. So VAC is the voltage from point A to point C. So A is going to be the red lead, C is going to be the black lead, and you'll notice it's across two resistors. So we're going to have R1 plus R2 over the total resistance. So the voltage from point A to point C is going to be equal to R1 plus R2 divided by the total resistance times 20 volts. That works out to 3.2K divided by 13.3K times 20 volts, which equals 4.81 volts. So the voltage at point B, or VB, is going to be equal to the ratio of R2 plus R3 plus R4 over the total resistance. So my voltage VB is going to be equal to the ratio of R2 plus R3 plus R4 over RT. So my calculation becomes 12.3K ohms divided by 13.3K ohms times the 20 volts. That'll equal 18.5 volts. So in table 5.3, I've entered all my calculations under theory. I try to keep all my numbers to 2 decimal points just for consistency. So under procedure, step 6, we're going to construct the circuit of figure 5.2 with the R1 equal 1K, R2 equal 2.2K, R3 equal 3.3K, and R4 equals 6.8K, but do not connect the power supply. We're going to set the DMM to measure ohms, and we're going to place the probes from point A to ground to measure the circuit's total resistance and record this value in table 5.3. So I've constructed the circuit of figure 5.2. This is my 1K, my 2.2K, my 3.3K, and my 6.8K, and I have not connected the power supply to my circuit. So the total resistance reading on the ohm meter is 13.34 K ohms. So in table 5.3, I record 13.34 K ohms. So if the total resistance measured of the circuit in figure 5.2 matches very closely the theoretical value we calculated, then we know that the resistor values are the correct values and we have them hooked up in the circuit correctly. So under step 6 of procedure, we're now going to connect the power supply with E equal to 20 volts, set the DMM to measure DC voltage. We're going to place the DMM probes across R1 and measure its voltage, and we're going to record this in table 5.3. We're going to determine the deviation and repeat this process for the remaining 3 resistors. Then we're going to calculate power dissipated by each resistor using the measured voltage and resistance, and we're going to record these in the final column of table 5.2. Remember to adjust your power supply for 20 volts. We had it at 10 volts, so now we need to use the voltage adjustment knob to increase it to 20 volts. This is the placement of the leads across the 1K ohm resistor to measure V1. And you can see the voltage drop across R1 is 1.505 volts, so I'm going to record that as 1.51 volts. So this is the placement of my banana leads across R2, which is the 2.2K ohm resistor. And you can see the reading is 3.239 volts, so I'm going to record this as 3.24 volts. So this is the placement of the leads across R3, the 3.3 k ohm resistor. And the voltage drop across the 3.3 k ohm resistor is 5.04 volts. So this is my placement of the leads across R4, and this is the 6.8 k ohm resistor. And the voltage drop across R4, the 6.8 k ohm resistor, is 10.15 volts. So on table 5.3, under measured, for the voltage drop across R1, I've recorded 1.51 volts. For the voltage drop across R2, I've measured 3.24 volts. For the voltage drop across R3, I've measured 5.04 volts. And for the voltage drop across R4, I measured 10.15 volts. Now under procedure, step 7, we're going to find the voltage VAC and the voltage at point B. So in figure 5.2, we can see that point A is at the top of the 1 k ohm resistor, and that's going to be the red lead. And point C is between R2 and R3, so that's the bottom of the 2.2 k ohm resistors. So this is the placement of my leads. This is the red lead, and it goes to the top of the 1 k ohm resistor. The next resistor down is the 2.2 k ohm resistor, and the lead goes at the bottom of the 2.2 k ohm resistor. So the voltage is being measured across two resistors. And you can see the meter is reading 4.74 volts. For the measured voltage drop at point A with respect to C, I measured 4.74 volts. So in figure 5.2, the voltage at point B, we're going to be putting our red banana lead from the voltmeter between R1 and R2. Doesn't matter which one you clip it to because they're connected together, as long as it's at the junction of R1 and R2. And we're going to take that with respect to ground. So my red banana lead with the alligator clip on is going to go between R1 and R2, so I've just clipped it to the top of R2. I just want to show you that the common from the digital multimeter is now connected directly to the common of the power supply. So that's the voltage at point B with respect to ground, or common. And you can see the voltage reading is 18.44 volts. In table 5.3, for the measured value of VB, that's the voltage at point B with respect to the common, I measured 18.44 volts. Under table 5.3, I'm going to leave you to calculate the percent deviation and the power dissipated by the resistors. I'm going to leave you to answer the questions at the back of the lab. So when you've completed your lab, leave circuit to set up and show it to your instructor, and then they can initial your lab to indicate that it is complete.